research scientist with Deeplite. Today I'm going to talk about the science of deep learning model compression. It's more of a tutorial kind of a presentation where I introduce what is the problem of model compression, give you a very strong background on different kinds of techniques that is available to compress a deep learning model, and then towards the very last section of the presentation I'll be focusing on what we do at Deeplite and how do we overcome most of these challenges, right? A very quick introduction of Deeplite to you. We are a startup. We are about 2 years old. We are based out of Montreal in Canada, and very fortunately and very proudly, we were listed as CB Insights AI 100 of year 2020, which means that in the year of 2020, all around the world, we were listed as one of the top 100 AI startups in the world. Yeah, so very happy about it, and that once again explains how important and how crucial this problem that we are trying to solve is. So that is the emphasis of today's presentation. I'll be very happy to keep this presentation an interactive one. Any kind of questions, however naive or simple it may be, feel free to ask a question. I'll be happy to explain it further and solve your doubts. And Nishant, since I am in the full screen mode, I'm not able to see a raise of hand or the chat window. So I request you to help me with that. So if there is any question or something, just stop me there so I could take the question.
Sure.
Thank you. Okay, let me introduce the domain and the problem to you, right? This is AI is such a vast field. AI started about in 1950 with the simple motive that we need to mimic a human brain and pass the Turing test, right? We need to automate stuff. That's sort of the fundamental goal of AI. And for roughly about a decade, deep learning is what is driving AI to new frontiers. And as you could see in the chart below you, the traditional machine learning achieved a performance with SVMs and random forests, etc. Neural network seems to mimic a human brain much better. And in today's world, with the help of deep learning, we are able to achieve human level performance in many applications and many tasks, right? Well, this is an excellent breakthrough in the world of AI and achieving the true sense of artificial intelligence. This comes with a cost, and that cost is what we need to focus right now. That deep learning is outperforming humans at multiple applications. However, we need more computation, much more memory size, and much more money than it was ever required in the past. Okay, as a very simple analysis, Moore's law says that there is a 2x improvement in the number of transistors a chip can hold every year, right? If we start from 2012, according to Moore's law, the hardware improvement or the complexity in which hardware computations grow is a size of 10x, right? But the deep learning models are growing at a size of 300,000x, and we simply do not have that much amount of computation to train a deep learning model. Let's keep it that simple, right? So in order to get better accuracy, in order to reach human level performance using deep learning models, you need to have more computation, right? So that's the kind of, so why is this computation required, right? Because of the revolution of depth. As you can see in the last decade, this is a very simple sample set of the growth of deep learning models, right? One of the earliest models was VGG19. It gave about 72% accuracy, occupying about 76 MB in memory, right? The disk size it takes is about 76 MB. But as the number of layer grows, right, from VGG19 to ResNet 152, the depth of the model increases. The model is becoming more and more deep, and the accuracy of the model is also increasing. But at the same time, the memory occupied of the model is also increasing, right? So what happens when this memory becomes really large? When we try to put a deep learning model in production, this is roughly what happens. Okay, there is an endpoint where we try to collect data. The endpoint could be your mobile phone, could be your wristwatch, could be an IoT sensor, could be a CCTV camera at the street, could be anything that collects data. Okay, so we collect this data and we try to send it to a cloud. Assume it's a CCTV camera, okay, that is there at the traffic signal. It is basically capturing every frame of image, and transferring this frame of image to the cloud. And at the cloud, we have a sophisticated server which hosts a large deep learning model, and this deep learning model performs two steps. Okay, it tries to extract features and tries to classify the particular frame of image that you have sent. Okay, and based on this model's classification, we are trying to perform a decision. Okay, let me quickly take an example of self-driving car. Okay, if we are trying to capture every frame of image from a self-driving car, send the frame of image to the cloud, uh, and the cloud, there's a deep learning model that tries to understand this particular image and take a decision whether to take a left or a right. Okay, this whole time that is required from data collection to decision making is what we call as the latency, right? And there is a huge problem with latency. That is what I'm going to show you in this video.
How reliable is artificial intelligence? It's a question that has come up a lot lately, especially with the rise of self-driving cars. Reaction time is a critical factor.
Yeah, so the problem is as simple as that. The reaction time is a very critical factor in applications like self-driving cars. If the latency was, sorry, if the latency was even 1 microsecond later, the car would have just simply crossed over the girl before the decision of stopping was taken. Right. So we need to start reducing this latency a lot, and one of the important ways to reduce this latency is going from cloud-based inferencing to edge devices. Sorry. So what I'm trying to say is that instead of collecting all of this data from the car, sending it to a remote server, take a decision on the remote server and send the decision back into the car. Why can't we take all the decisions inside the car itself? So we should host a very small GPU inside the car, and this GPU should be capable of performing all the computations that we need to perform, and the decision can be taken inside the car itself. So this is what we call as edge computing. But one of the problems with edge computing is that the edge devices or the small GPU that we are trying to host in a car is severely constrained by its memory. Typical memory size would be less than 1 MB. Um, its power consumption is less than 10 watts. Its computational complexity is typically less than 10 teraflops, and its cost is $10. Okay, let's take the first row just to understand it much more, right? We saw that the typical models here are of the size 76 MB to roughly around 230 MB. Okay, a very average model is of this size. 230 MB is the size of a model, whereas an edge device has a total memory of less than 1 MB. How could we put a 230 MB model into a 1 MB device? And it's not just putting the model, right? We need to do some in-memory computations to process the input image and take a decision on this chip itself, right? So that is the kind of problem that we are facing, that the deep learning models are really exploding in size, and there's a revolution of depth happening. However, the hardware architectures are really small that we cannot really put these deep learning models onto the hardware devices. And as long as we do not put these deep learning models onto the hardware devices, we need to still go with the cloud-based solution. And you saw that the cloud-based solutions could be a question of life and death in many situations. It is a problem that important. Okay. Any questions so far?
So Sumit is asking if will 5G help with latency?
See, again, you're trying to improve the bandwidth, but as long as you have to send, say for example, if the CCTV camera in front of a self-driving car, okay, in front of a self-driving car, you have kept a camera, and that is capturing at a frame rate of say 10 frames per second, okay, that means that at every second you will have to send 10 frames of data to the cloud. The cloud has to compute 10 frames of decisions and send those decisions back to the car for all the 10 frames, and the car has to take a left or a right based on the decisions for these 10 frames, and this has to happen the next second also. So every second this whole costly computation of sending data and receiving the decisions back has to happen. If there is a small bandwidth problem at any point of time, or if there is a network disconnection at any point of time, even for 1 second, you have basically lost all the decision making capabilities on your car, right? Even if it is 5G, it will not help the problem, because this is a very very critical problem that we are trying to solve.
The other question is from Ashish. There's a trade-off between accuracy versus latency. How do we maintain the accuracy at edge?
Yes, so that is the exact problem that we are trying to address. That is there a way that we can compress the model, make the model much smaller, and without compromising on the accuracy of the model? And that is why the problem is very challenging and very important. And that is what I'm going to talk about in the rest of this presentation. That how do we compress the model without sacrificing the accuracy?
Sounds good. There was one person who had raised hand. If you
Yes, please.
okay, yeah, Rajiv.
Yeah, so from a hardware perspective, there are three types of hardware that we are seeing with respect to acceleration. GPUs is one of them.
Mm-hmm.
ASIC is another one, and then FPGAs is another one area.
Correct.
So I have recently seen some very good results coming out of FPGAs at very less, probably. If you look at the CPUs, they are probably in the higher milliseconds, probably 500 milliseconds and above. If you take GPUs, they are in the range of 100 or probably 50 milliseconds to 500 milliseconds. And if you take FPGAs, they are predominantly in the lower level of ASIC and ASIC, and FPGAs are in the range of probably microseconds to probably 50 milliseconds type of a range. So are you aware of any cases where such hardwares are being today used in autonomous vehicles? I know ASIC is there because Tesla and all has its own design.
Yes. A very quick comment about it. Again, there are so many self-driving car applications where people are trying to use different hardware architectures. But as of today, one of the common architectures that we are trying to use in a self-driving car is sort of a Xavier GPU. We still tend to go with GPU, but the GPU is still of smaller size, right? Like less than 256 MB to 1 GB kind of a space. Okay, the reason of still going with GPU is two reasons. Okay, the first reason is that the self-driving car has enough capability to host a small GPU, so why not go with the GPU? And second thing is that it's we it is not a single deep learning model that's going to run in a self-driving car. We are going to run at least 100 different deep learning models, a couple of classification model, a couple of object detection model, a couple of segmentation models, and then a couple of video time series analysis models. So at least 50 to 100 different deep learning models are to be hosted in a single self-driving car, and a combination of these deep learning models decision is what we are going to take. So holding FPGAs inside a deep learning model is good, but it is not sufficient to solve the problem that we have right now. However, having said that, there are lots of healthcare and manufacturing applications where we are seeing a predominant growth of FPGAs and RISC CPU cores. And I'm going to briefly talk about some of the different hardware applications that we have worked in the slides going forward. So I hope that will help to answer these questions better.
Yeah, thanks. I hope the question is answered. There is, one again. Won't AutoML help in model compression? I
That
you might be talking about that.
Yes, yes, that is my favorite question. So whoever asked that question, thanks for asking that question, and just hold on to that question. Okay, I think in the fourth slide from now, I'm just going to answer that question. I'll take the help of that visual aid in that slide to help you answer the question. So just please hold on to that.
Sounds good. Please continue.
Okay, wonderful. So we saw what is the problem, right? The problem is that we need to start taking these deep learning models and putting that into edge hardware devices. Okay, and some of you have asked the right questions of what are the challenges of doing this task. It is not going to be an easy task. I'm now going to highlight in a very structured manner what are the exact challenges that we are facing with going to a hardware device, okay, or deploying the deep learning model into an edge device. Okay, the first is democratization. Okay, and this is going to be a passionate topic for me. If you look at some of the recent models from some of the big companies that you know of, right? Nvidia came up with this model for text processing, which is which is, I think, is OpenGPT 3 or OpenGPT. The model that Nvidia came up with is called Megatron, and it has 8.3 billion parameters. Okay, and Microsoft came up with the a following model that performs better than Megatron, and it has 17 billion parameters. And OpenAI came up with this OpenGPT 3, which is supposed to be the state of art model. It has 175 billion parameters, 350 GB in size, and $12 million to train a model. Okay, forget about edge devices. Okay, let's take that out of discussion for a minute. Even if you want to train it on a cloud based architecture and cloud based solution, not not everybody in the world could afford a supercomputer having a capability to compute a model of size 350 GB, okay, and having 175 billion parameters, and not many could afford $12 million to train. Okay, so recently I've been talking about this in social media now and then, that many of the recent research papers, right, that comes out, if you want to reproduce the results of the research paper, not many of us can do it. Only the likes of Google or Microsoft or OpenAI can do it. Only they can afford to spend in so much cost and build a series of TPUs or GPUs to train or test those models, and those models are out of reach for almost 90% of us, right? So in a world where we want to ideally democratize deep learning, when I say democratize deep learning, everybody has equal right to a deep learning model. Okay, as of today, we do not have that equal right. Not many of us can use these deep learning models because it is simply out of reach for all of us. Even if you want to use a GPU, okay, forget about using these in an edge hardware device. It is totally out of question of how do we want to put this in an edge hardware device. So the first challenge is how do we democratize deep learning and make it available to everyone and all devices. Okay, and the second thing that we need to focus is one of the questions that was asked, that we need to start focusing on multiple metrics while we are using a deep learning model. Okay, often the only metric that we are focusing right now is the accuracy of the model. Okay, if the accuracy is better or is it good enough, it's good enough for me. But when we want to put these models into production onto a deployable system, then there are so many other parameters that we need to consider, right? Like, first is the number of parameters of the model. Second is the number of computational flops. When I say computational flops, it is like the number of arithmetic operations or floating point operations the model is performing. The third is the size of the model, how big or small this model is. The fourth and fifth are the training time and the inference time. And the sixth one is the energy consumed by the model. This is again one very important factor that recently, I don't know how many of you are following the whole Timnit Gebru's discussion in Twitter and in social media. One of the important research aspects of Timnit Gebru was, she highlighted how much energy inefficient training these deep learning models are. Okay, in one of the papers by Struble, she pointed out that the the amount of energy that Amazon or Microsoft or companies like that are using to train their deep learning models over a year is more than the total fuel consumption by the entire of America over a year, right? So take all the fuel consumption by America over a year. Amazon and Microsoft is consuming more fuel than that to consume energy to train their deep learning models. Right. So that is also an important factor that we need to start considering while we are trying to optimize a deep learning model or use a deep learning model. Okay. So just don't go behind the accuracy only. Okay. The third is again one of the important things.
Right. To summarize, so there are 6 of these metrics that we are concerned with, right? And just counting them on figure, and all of them need to be paid attention to get a proper optimized model.
Exactly. And whenever we want to propose a better deep learning model, don't say that it is the new deep learning model is better in terms of accuracy. We should also compare the existing models and the new model in terms of these other 6 parameters as well. That becomes an important benchmark. Okay. The next is again multiple hardware support, right? I think this was again one of the very valid questions that was asked. We have different hardware architectures. We have RISC CPUs. CPU architecture is one, and we have multiple different CPU architectures, ASIC architectures, RISC architectures. We have GPU architectures. We have different microprocessors like FPGA. What we need to try to do is that when we are trying to optimize the deep learning model, we need to make sure that the optimized deep learning model or the smaller model is compatible with multiple architectures, right? If I want to put this model in a GPU, I should be able to put it. If I want to put it in a CPU, I should be able to put it. If I want to take that model and put it in an FPGA, I should still be able to put it. So that is also one very important problem. Again, if you are trying to only focus on CPUs, it doesn't solve the problem of optimization for us, because there are so many applications that uses FPGA and other kind of hardware architectures that we should make sure that we support all different types of hardwares or as much as possible. Okay. The next is the problem of optimization itself is very difficult. That as most of you pointed out, the accuracy of the model decreases. That is point one. And the second point is, generally in the world of deep learning, we know that there is a lot of hyperparameter tuning kind of a problem, right? So there is a lot of manual labor and back and forth and trial and error kind of approaches that exist in trying to optimize the deep learning model. Let me try to remove this one layer. Let me try to remove these few parameters. Let me try to optimize the model in this direction, in that direction, etc. Right? So instead of trying to do a lot of extensive trial and error or brute force kind of approaches, can we have a reusable black box kind of an approach, which just simply optimizes your deep learning model without giving you much of a struggle in doing that. Okay. And this is again one of the challenges that I highlighted, that most of the research papers today are not reusable, and most of the research papers cannot be translated into production because they are really costly to use, right? Not many of us can use it in production environments. Okay, so these are the 5 challenges with why we cannot so easily optimize a deep learning model. And if you have understood the challenges and appreciate all the challenges, I will quickly go through the different solutions that exist in the literature to optimize the model. And Nishant, I think at any point of time, if there is a question, feel free to stop me.
Yes, so there are. There's a question from Saurav. He says that he asked that does your model compression algorithm help during training also, like training a 1 billion parameter model?
Yeah, so there are 2 kinds of compression approaches broadly, which is called on-train model compression and post-train model compression. Depending on the application that you're trying to use, we could do both of them. But one of the popular approaches that exist as of now is what we call as the post-training model compression, where we say that okay, training is a one-time task typically. I will train the model in a super GPU kind of an environment, train it completely, get good accuracy, and after training the model, I'll just compress the model once, make it really small, and put that small model into my edge hardware device and do the inferencing there. That's kind of a popular solution that exists, but there are lots of papers that talks about how do we reduce the parameters of the model during compression also. Sorry, during training also.
So you would be talking a bit more about that also?
Yes, yes.
Okay. And Ashish is commenting that critical applications, self-driving healthcare, is accuracy the most important criteria?
Correct. Accuracy is absolutely the most important criteria, right? No doubt about it. But and I'm not going to say that we are going to compromise on the accuracy at any point of time. But what use are these deep learning models if we can't even deploy it in an edge device, right? If we can't even use them, the deep learning models that we know of today is only as good for a research paper. Okay. After a research paper, these deep learning models are going waste, and we are not even able to use them in a production environment, right? While accuracy is the most important criteria, usability and democratization is almost as good as accuracy itself, right? So the model has to be accurate and also usable in production environments.
Sounds good. Yeah, please continue.
Okay, wonderful. So let's quickly go through what is the basic idea of optimization. Okay, this is a very toy example of a CNN model. If you look at the model, there's an input layer where an input image is given. There is a convolution layer, pooling layer, dense layer, and output layer. Okay, so if you look at this particular figure, the convolution layer and the dense layer are the only two layers in this model that has parameters or learnable parameters or trainable parameters in this model. Okay, the pooling layer is a simple mathematical function that doesn't learn anything through the architecture. So so the idea of optimization is that given a deep learning model, we need to identify these trainable layers in the model, and after we have identified the trainable layers like a convolution layer and a dense layer, we try to reduce the number of parameters in this layer using some technique such that the model becomes smaller but the accuracy is the same. Okay, so this is the very basic one-liner idea of what optimization performs. Okay, and there are four different school of thoughts in terms of model optimization. The first is called parameter removal, where we try to remove certain parameters from these layers. The second is parameter search. We search for better parameters. The third is parameter decomposition. We decompose existing parameters into smaller chunks. And the fourth is parameter quantization. Okay, and these are the four things that I'm going to talk about now. So let's focus on parameter removal for now. Okay, what is parameter removal? Parameter removal is a thing.
It might be for the audience to just stare at this slide a little bit more so that they broadly know. So there is parameter. There are four broad ways: parameter removal, search, decompose, and quantize. And each of them is a vertical in itself, right?
Correct. And I'm going to go in depth of each of the verticals. So I'll be talking about them in the going slides.
Okay, sounds good.
Okay. So let's focus on the first vertical, which is parameter removal, right? And see what it is and what is there in the vertical. Parameter removal is nothing but pruning of weights. Okay. When I say pruning of weights, I hope everybody in this audience is aware of what a convolution layer is, and suppose a convolution layer has 6 kernels or 6 filters in it. Okay, so these are the 6 filters in a convolution layer. Okay, each filter has a size of 3 cross 3. So there are each filter has basically 9 weight values. Okay, each is a 3 cross 3, and each cell in this matrix is basically a weight value, and we are learning all these weight values. Okay, in weight pruning, in parameter removal, what we are trying to do is take a particular parameter and replace it with 0. So whichever place I have shaded with blue is basically made as 0, and only the weight values that are marked as white color cells are used to perform the forward computation. So when we do a W transpose X, multiply the weight with the input X, we basically do not use the blue shaded ones. The blue shaded ones become 0. Okay, so there are different ways to do it. The first one is what we call as random weight pruning, where we take some random weights and make it 0. So there is there is this blues at random places. The second one is what we call as a column pruning or a shape pruning, where we give a predefined shape or an architecture or a particular column kind of or a row, where we say that okay, this entire column or this entire row or this entire shape is made zeros in all the filters that I have in my model. Okay, so in all the filters that I have in my model, make the first column as always 0. Okay, so that is what we call as column pruning or shape pruning. The next is what we are focusing on is the entire channel pruning. Okay, so here is the example. Okay, say suppose a particular convolution layer has 5 filters. Okay, and what we are trying to do is that instead of removing certain weights inside a filter, we try to remove the entire filter itself. So instead of having 5 filters, we will now have only 4 filters. Now before I go into this, right, I need to focus on this slide a little more and explain one point. Okay, um, in these kinds of weight pruning technique, again it is very important. It will answer a lot of questions, so just focus on this one slide. uh, when we are trying to remove these weights, we technically do not remove them from the model, we just replace that values with zeros. Okay, so if say, so for example, an original model had 100 parameters. Okay, after removing or pruning these weights, the pruned model will still have 100 parameters, except for the fact that 50 of the parameters are made 0, but my model will still have 100 parameters, and computationally I still have to multiply my input x with a 0 weight, so x into 0 happens. So the number of computations is also not reduced, and the number of parameters of my model is also still 100. So what we call this kind of parameter removal technique or compression technique as false pruning. Okay, so in research papers, people report that 80% of my weights are zeros. Okay, it is good that 80% of your weights are zeros. However, still, my model still has all the 100 parameters, so my model size is not reduced. While storing in my disk, I have to store all the zeros also along with the model, and also while performing computation, that is arithmetic operations, I still have to multiply my input with a 0. So though 80% of my weights are removed, the size of my model or my inference time or my computational flops have not reduced at all. So that is why we call it as false compression or false pruning. And in fact, most of the research papers that exist today in pruning does what we call as this unstructured pruning. Right? These are called unstructured pruning, and it does not reduce the number of flops or computations or the size of the model.
It's great that you raised this point, and I don't think the term false pruning or pseudo pruning is popular anywhere. It's well known anyway, so we should try to make it more popular. That all you guys are doing is pseudo pruning.
Yeah. So we write a lot of blogs about it, and in every paper that we write, we highlight this pseudo pruning kind of an approach, and that's the pain point, right? There was even a recent paper in CVPR 2020 which said that they're able to achieve 92% pruning. Okay, that means that my model is only 8% as small as the original model. Okay, it should be technically, but even though they have attained 92% pruning, the size of the model or the computational flop of the model has not reduced at all. It is the same, and it takes the same time, it consumes the same energy. All my other parameters are exactly the same, right? Only that they have replaced 92% of the weights of my model to 0, and it doesn't help me in any way in putting the model into production. Right? The only real way of doing pruning is that instead of putting certain weight values as zeros, remove a complete filter from the layer. Okay, so instead of having 5 filters, we have only 4 filters. So typically in your convolution layer, when you define it, we will say 512 filters or 256 filters or 1024 filters, right? So instead of having 512 filters, we now only have 100 filters. We have removed 412 filters from that layer. Now, doing this operation will reduce the size of the model and also the computational complexity of the model, but unfortunately will severely reduce the accuracy of the model also. Okay, so removing a particular complete filter from a layer is very sensitive to the model and will also reduce the accuracy of the model. So this is the only approach where there are few papers in the literature that they have talked about, of how can we remove few filters from a particular layer or many layers. But then this also becomes an NP hard problem because we do not know if there are, say, ResNet 152 has 152 layers in it. Okay, out of which about 140 layers are convolution layers. Out of the 140 layers, from which layer how many filters to remove and what filters to remove. Okay, so this problem becomes an NP hard problem. People have come up with some approximate solutions, but it is very hard to use it without reducing the accuracy. Okay, some of the techniques that exist says that I'm able to reduce the model size by 20-30% by reducing 5 to 7% of accuracy. But removing 5 to 7% of accuracy could be very crucial in many applications. So how much practical usability this technique has is a question in itself. Okay. Again, the kind of pitch is going to be, I'm going to explain different techniques that exist in the literature, a broad overview of them, and the challenges including them, because all these challenges will lead up to what we do at Deeplite and how do we solve this problem in a better manner. Okay, so that's going to be the pitch of this entire tutorial. Okay, and yeah, many people asked about NAS techniques and AutoML techniques. Okay, let me
Yeah. So there are a couple of questions
yes.
streaming in. So some, I think, okay, I have to now combine questions because there are 4 or 5 questions. So I think Abhishek and Shreyas noted that you could use sparse matrices which are efficient, and you could go that route and address that false pruning problem. We can reduce the speed of computation. Yeah. So do you have something to say about that?
That's a wonderful question. Okay. If we have sparse pruning, libraries like SciPy provides us a better way of storing the sparse matrices and also performing computational sparse matrices. Right. Very unfortunately, the hardware compiler stack that we have for deep learning is so naive that it doesn't support any of them. We need a complete revolution of the hardware stack. Let me explain that a little more. Okay, in libraries such as PyTorch or TensorFlow, we do not have what we call as a sparse convolution. Okay, so we have only dense convolution. So the convolution doesn't happen that doesn't happen efficiently for a sparse matrix at a PyTorch level. Okay, let's go one layer below, right? Libraries such as CUDNN or CUDA doesn't support sparse matrix multiplication in most of the cases. Okay, CUDA in the recent version has a sparse matrix multiplication capability, but it still doesn't work well for most of the deep learning models because um, yeah the capability doesn't exist today. And the other problem is, even if a compiler supports it, the underlying hardware has to support it. Okay, and in many of the existing cases the hardware doesn't support sparse matrix efficient sparse matrix multiplication. So in order to make this technique a reality, we need to change three things. Okay, first we need to come up with specialized hardwares, which doesn't exist as of today in most of the cases. Second is, then we need to come up with specialized compilers that could compile the model efficiently to perform sparse computations. And the third is, libraries such as PyTorch or TensorFlow should support it out of the shelf for you to use these convolution layers in your model. Okay, so unless otherwise we change this entire stack, this kind of pruning is not a reality today. And there are some kind of a startups working to make this a reality, but it what I'm talking about is complete change in the hardware altogether, right? A totally new FPGA or a totally new CPU architecture, which is going to take sweet time. It is not a year's worth of time.
Right. But I think it will be useful to comment that sparse multiplication all the way from the GPU level to there's a lot of research happening on that and better GPU kernels. Is that right? Are you happy with them, or they are just very primitive?
They are still very primitive because I have not seen a single model in production yet. There are a couple of startups who are working full time on this for sure, but we are still far away from making this a reality. I think that's the comment that I want to put forth.
I see. There's another. So I've been trying to. I think Abhishek, Shreyas. Your questions have been answered. Hetul, your comment I think also has been answered. If you think otherwise, please feel free to comment. Shabir has a comment that there are some metrics used to perform filter pruning, L1 norm, correlation between filters. Right, okay, and Pankaj is asking, instead of removing a filter, can it not be handled during hyperparameter search?
Okay, let me first answer Shabir Basha's question. Okay, yes, techniques. That's what I was presenting on this slide. That techniques exist for pruning different layers. But also, if you look at the papers that talks about these techniques, they clearly show a 5 to 7% decrease in accuracy. Okay, in many of the models. So, if you look at the papers, the tone of the papers will be something like this. Again, nothing to take away from the papers. What I'm trying to highlight that this entire research problem is still in a nascent stage, that we have to go really far ahead to make it usable in practical environments. That in toy examples like MNIST, CFAR 10 and CFAR 100, using VGG 19 and ResNet 18, they will be able to achieve good pruning without decrease in accuracy. But when we start using the same pruning techniques like L1 norm based or correlation based pruning techniques to larger models or more complex object detection models or segmentation models, the accuracy of the models fail completely. Okay, so in most of the practical environments, we use these kinds of object detection model or a segmentation model or a post detection model, etc. And pruning those kinds of models is very tough as of today.
Yeah, I've handed the mic to Shabir. Maybe he has something more to say. Shabir?
Hi Anush, am I audible?
Yes, you're audible, Shabir.
Yeah, Anush, I have seen one paper where they have reported the results over object detection task also.
Yeah.
But
Again,
even I can see there is no not much reduction in the performance when compared with the base model.
mhm.
That paper got accepted in WACV 2020,
Okay.
and it is from IIT Kanpur.
Okay.
I'll just text that paper. The title of that paper is leveraging filter pruning for deep model compression.
Sure. I'll be happy, but again, I am not trying to take away anything from the research papers that exist. Okay, and there are so many research papers on this topic as of today. Um, However, in practical scenarios, that what most of us found is that many of these techniques are not generalizable across models. Okay, and that is one of the reasons why these techniques are not extensively used in production. Right? If this was possible and if it is as good as using a technique to compress a deep learning model, people would have used it left, right, center today. Right? You could have seen it in almost every single product that comes out. But we are not able to use it because of what we highlight as the generalization capability, that it works, certain techniques works on certain groups of models, certain techniques works on certain other groups of models. But when we go into a production system, it's very difficult to write these kinds of rules into a production system to prune the model automatically.
Anush, one last question from my side. Can you please go to previous slide?
Yeah.
Yeah, here, if you can see this blue points.
Mm-hmm.
So I have gone through the papers where this parameter pruning is happened in the fully connected layers, and that is dense layers.
Mm-hmm.
But as far as this convolution layers are concerned,
Mm-hmm.
if you make some of the weights are zero here,
Mm-hmm.
then the corresponding pixel value will doesn't take into the account.
And the corresponding pixel value is so the way the matrix multiplication is happening right now is that the corresponding pixel value is taken into account. So
But it is multiplied with zero, right?
we still do x into 0 and put it is equal to 0. So a multiplication operation is happening there.
No. Though it is happening,
Yeah.
what I'm saying, during this forward propagation, this let us assume this first weight filter value.
Yeah.
These 3 pixels will not come into the consideration of forward propagation, right?
So what do you mean by not come into consideration, right? It is
Because, for example, let us assume these pixel values are some ABC.
okay.
Now, these ABC values are getting multiplied with 0 here.
Correct.
A multiplied by 0 plus B multiplied by 0 plus C
Correct.
multiplied by 0.
Correct.
So that A, B, C is not getting into the account, right? While
Yeah, that is okay. But how is that helping me in reducing the size of the model? Uh, uh, as zero is still stored there, and the multiplication is still happening there, right?
No, I am not talking in terms of compression. I am just saying this method will not take some input information into account.
Yeah, we take the ABC, multiply it with zero, and put the result as zero. That is true. That is happening. But we can use this more efficiently only when we have efficient sparse matrix multiplication capabilities.
Yeah, I think so. So Shabir, you might have to think a little bit more deeply about this problem. Even though the zeros are there, they are not being fully used as such, and unless we have this sparse machinery. And so, okay, so let's continue.
Please.
And Professor Sumit, I completely agree to you, right? That is what I'm trying to highlight, that as of today, using these the unstructured pruning or zeros in production environments today is little tough. However, going forward, people are working on it to come up with new emerging architectures, right? And that's the point that I was trying to highlight, that existing architectures and compiler stack doesn't support it. But as we go into the future, there are emerging architectures and corresponding supporting compilers for that. And as you can see here, that in DARPA and IARPA in their agile program have made it as a 2030 challenge, right? That means that it will take roughly about a decade for them to build this whole stack, and that is actually good. We are progressing in the right direction, but we are not there yet today. That's what I'm trying to address.
Awesome. Thanks for your comment, Sumit. Yeah, so there are no more questions. Please continue.
Okay. In terms of parameter search, so this is a very naive approach of how do we do parameter search. Okay, we take a model, the first blue model with a yellow accuracy. Okay, the yellow accuracy means is roughly about 75% accuracy. Okay, we mutate these models to bring about 3 different architectures. Okay, the bigger architecture, one architecture, second architecture, and third architecture. Okay, and we take these 3 architectures, train these 3 architectures again from scratch. Okay, and after training these 3 architectures, we find that the model on the top has the best accuracy. Okay, on the model on the below. Okay, so we take these 2 models, keep the best models, and then we mutate again. Okay, uh, and we keep on doing this. So if you look at it, instead of training one model, what I said to you initially, that training the initial model itself is a pain for me. Now what AutoML or NAS is eventually saying, that instead of training one model, you go and train 100 models, and 100 models which are maybe little smaller or as good as the original model. Your NAS is as of today is a intractable problem to use in a practical real world application. It is heading in a really good direction. People are coming up with efficient NAS and real time NAS and uh, NAS for hardware constrained architectures, but we are still progressing in the direction. Okay, it is again, we are very far in practicality from using these NAS techniques, because this NAS techniques would take a real good time to be used in a real world environment. Okay, again, to comment, there was this ICPR paper in 2021 where Google came up with an efficient NAS technique, and their efficient NAS techniques takes about 12 years to train a deep learning model. They used some 100 GPUs to reduce the time, 100 TPUs to reduce the time of 12 years. Okay, but if I had access to only one TPU or two TPU, it will take roughly about 10 to 12 years to search for a good architecture, right? And there will be no client who will come to you and say that, hey, I have a big model, I cannot put it into this hardware, could you help me? And I cannot ask them that, okay, I can do that, will probably come after 10 to 12 years, right? And I'll give you the model. That is where the practicality of this problem that I'm talking about, and that is the problem with AutoML and NAS as of today. It is promising, but again, in real world and practical environments, we cannot use this, because instead of training one environment, we are trying to, in this particular example, we are training 20k other models, 20,000 more models, to find out which is the best model.
There is a question about distillation. So, are you going to also talk about how effective distillation is?
Yeah, I mean, distillation is one solution that is used to train these models, okay, so that the accuracy is achieved. So the original model is used as a teacher, the new mutated model is used as a student, and using this teacher-student kind of a setup, we try to train the student to achieve better accuracy. Okay, so distillation focuses again on how do we improve the accuracy of the student, but again, it doesn't help us to optimize on the other parameters that we have.
Okay.
So in this whole space of parameter search, the problem that we have is the search space is so large that it takes us so much time in searching for the best architecture out there that will help us with the constraints that we have, and it is very difficult for us to search for the good model in a practically limited amount of time. Okay. The next idea is decomposing parameters. In parameter decomposition, the idea is something very similar to SVD, that we can take a matrix W or a tensor W, and we can decompose it into a set of singular matrices, USVT, where U and V are singular matrix and S is a diagonal matrix. Okay, and the more U has a particular rank, when we use U as a full rank, we basically get the W as such without any loss, but we can reduce the ranks of U and V to get a good approximation of W. Okay, so this low rank approximation of U and V will help us to reduce the number of parameters in W, but achieve a good approximation. So this kind of SVD or tensor decomposition or dictionary learning kind of approaches is good to reduce the number of parameters in a particular weight layer W. However, finding what is the low rank approximation is again a challenging task. It is not very straightforward to find the best low rank approximation. Techniques exist for everything that I'm saying is difficult, but even though techniques exist, I would not say that these are solved problems. Okay, I think that's the tone that I'm trying to say. That in every problem, there's a lot of research that's going on today, and in every conference, there are at least 5 to 10 really good papers that are trying to improve the problem solution overall. But having worked in this space for almost 5 years and having seen so many different custom architectures and custom data sets that people are trying to use, if I take the solution that exists in the paper and translate it to a real world problem into a production system, it becomes really challenging. It is not very straightforward. Right. Yeah. So this is same as SVD, a different chart. Okay. The fourth vertical that I am focusing on is on parameter quantization. Okay. So parameter quantization is an interesting technique which says that I will not remove any parameter from my model. Okay. All the parameters. If my original model had 100 parameters, I will still have 100 parameters in my quantized model, but I will reduce the bit precision of each of the weight values. Okay. So each of the weight values as of today by default is represented as a FP32 weight value. Okay, floating point 32 takes about 4 bytes of memory space. Okay, so each single parameter value that I am storing takes about 4 bytes. What if I reduce these 4 bytes? Okay, so if I can quantize these FP32 values, to int 8 values, okay, ranging from -27 to +127. I could basically reduce the size of the model by 4 times. Instead of having 32 bits or 4 bytes to save the value, I will now use only 1 byte or 8 bits to store the value. Okay, uh, and that is the whole idea of quantization, that can we reduce the bit precision of while doing it. Okay, and there are two questions here. First question is, will this bit precision reduction, like changing FP32 to int 8, will it reduce the accuracy of the model? That is question 1. And question 2 is, will all the hardware architectures support int 8 multiplication? Okay, the first question is what different research papers are trying to address, and if you look at some existing off-the-shelf solution like TensorRT, etc., that provides you capability of quantizing a model to int 8 uh, precision. Okay, but the question is, does all the hardware support int 8 multiplication? That the answer is no as of today. As a matter of fact, the most popular CUDA architectures, the CUDA compiler itself doesn't support int 8 multiplication. Okay, uh, what happens is, say for example, if I quantize a model to int 8 precision value, reduce the model size by 4, and give it to a CUDA based compiler, okay, what we typically use in PyTorch or TensorFlow, um, the CUDA internally explicitly typecasts these values from int 8 back to FP32, performs the matrix multiplication in FP32, and then typecasts it back to int 8 and give you back the results. Okay, so the idea of reducing the memory is totally lost here, because there's an explicit typecast that happens. Okay, why does the explicit typecast happens? Because in some cases the compiler stack doesn't support it, and in many cases the underlying hardware doesn't support int 8 multiplication. Okay, and again, people are trying to come up with different hardwares and emerging architectures to support lower bit precision multiplications. And one of the very important research work that is going on as of today is, how do we reduce the model precision from 32 bits to 2 bits. Okay, that literally means that I I need either a 001011 or a 01 to represent each of my weight value. Okay, and I don't need more than that. It is as cool as that. And there are lots of research papers that talks about how we can reduce the bit precisions to 2-bit encoding. Okay, if we are able to achieve this 32 bits to 2 bits, you have literally reduced the model accuracy size by 16 times. Okay, so if my original model was 16 MB, my quantized model will be 1 MB. Okay, that much amount of compression that you can achieve, and if we can do this without reducing the accuracy. Okay, and this is again a problem in research as of today, and people, it's, since the hardware doesn't support it, it's very difficult to put that into production.
So I have a quick question here. So we are working mostly models with 32-bit or 16-bit, and that's the best, partly because of the hardware constant. But when you go down to 2 bits,
Yeah.
is there an intuition there? Why is that information enough to do all these real world tasks?
Yeah, so when we do 2-bit encoding, Nishant, the point that we need to understand is we do not use just 2 bits. Okay, so if there are 2 bits, that means there are 4 unique values, right?
Sure.
So what we are trying to say is that in a convolution layer, each weight value is unique, in the sense that if I have 100 weight values, all the 100 weight values are different and unique values. Okay, in this 2-bit encoding, what we are saying is that instead of having 100 unique values, let me have only 4 unique values, and each of the weight value in that layer is one of these 4 values. So I need to store only 4 unique weight values, like it is shown here, and the kernel could be basically replaced with an index of this weight value.
Yeah. So that's the principle of quantization. But what
Correct.
I'm wondering is that what makes people think that 4 unique values would be enough to do image classification or find objects?
Yeah, so the idea is that even if you look at the weight value distribution, right, in many layers they are not very far away from each other. The weight values will be something like 0.95, 0.93, 0.91, 0.96, etc. Okay. So what if I can group all these 0.91 to 96 weight values as 0.93? Okay. So I am changing only a small amount of the weight value, and after changing it, if I retrain the model, right, the weight values of the remaining layers will get adjusted around this thing. That the weight rebalancing happens in such a way that this 0.93 approximation of 0.91, 92, 94, 95, 96 is enough.
So it seems that people have plotted histograms of these values, and all that clusters are, there are very few clusters that remain. So
Correct. That kind of histograms are very well established. That these kinds of histograms exists for deep learning models.
sounds. So if Bharat is asked, does that mean there's no gain in inference time due to precision training due to typecast in CUDA?
No, yeah, there is no gain in inference as of today in CUDA. That is true. That is a very true statement. And I have first-hand run quantized models in CUDA and found that there is no gain in inference time.
So we are all, it seems, waiting for sparse hardware and for quantized hardware.
Yeah, so
low precision hardware.
Basically, we need a better compiler stack and a better hardware or specialized hardware to make these compression techniques work. Okay, and the compression techniques that is not hardware dependent are so difficult. Either they are intractable problems or NP hard problems, or they are really sensitive on the accuracy. They reduce the accuracy, right? So yeah, so either we need to make those intractable problems tractable and practically feasible. That is point one, or we need to come up with a better robust technique of removing the channels or filters such as the accuracy doesn't drop, or the third is come up with a better stack or compiler to do that.
Yeah, all hard problems.
Yeah, so again, while I'm highlighting all these problems, the point that I'm trying to convey here is that these problems are so difficult as of today that we cannot practically use it, but that doesn't mean that there are so much of good research work going on around all these problems that people are trying to solve it as we speak now, right? So we will surely and eventually solve this problem, but can we use these solutions today? That is the only question for which the answer is no. We cannot use them today, right? And that is exactly where Deeplite, we are trying to mitigate these problems in some way possible, that we can offer a solution today in compressing deep learning models. Okay. And what we do is a very classical statement. We are trying to use AI to make the other AI models smaller, faster, and more energy efficient, both in the cloud as well as at the edge. Okay, and this can be used across multiple applications. And we proudly say this is possible because we have run multiple use cases at multiple practical situations with multiple clients, and we have really got good results so far. Okay, and like what I have told in one of the initial discussion, the way that we handle optimization as of today is what we call as a post training optimization. That there is somebody who takes the code and the data, uh, designs a deep learning model, trains the deep learning model, and provides us with a completely trained deep learning model. Okay, and what we do is take the trained deep learning model, compress it, and then deploy it in a real world environment. Okay, so the solution that we have in the market today does not focus on compression during training. We focus on compression post training. That solves some of the problem in the market as of today. It doesn't solve all the problems, but I think that's the first good step that we have taken towards that. And the compressed model that we provide could be deployed back into the cloud also, or it could be ported into any edge devices as well. Okay, yeah, and we also provide a complete black box optimization setup where it is very easy for people to compress the model. Okay, all you need to provide is your pre-trained model. Okay, and after providing your pre-trained model, there is a simple setup where you can provide these multiple constraints for optimization. The first constraint could be like, what is the acceptable accuracy level? Okay, and you can say that my accuracy should not drop below 0.5% of my original model. If my original model was 90.5%, my compressed model should not go below 90%. Okay, so that is something that you can set. And the second is you can design some constraints. Okay, what is the primary focus? Do you want to compress the model size? Do you want to compress the speed, reduce the speed of inference or inference time, or do you want to reduce the power consumption? And in today's version of what we have in the market, you can choose multiple of these options also. Choosing these options helps us to guide the optimization in such a way that these parameters are optimized. Okay, and of course there are different modes of search. You can do a deep search, a simple search. For example, a simple search would give you approximate results but in a very quick time. A deep search will go and search for the model in a deep manner. It will take a little more time for you to search it, but it will eventually come up with a much better model, a much better compressed model. And then we'll compress the model and we'll give you these things, right? Like we got 46 times compression, 4x times speed up, 5x times power reduction, and with only a 0.3% change in accuracy. That is what we are trying to achieve as of today. Okay, and that is what we have achieved also. Okay, the way that we do it is something like this, that the input information that the end user provides is the original training and testing data, and the pre-trained model that the user has trained with, and also some user constraints, right? What is the delta of accuracy, what is the target size, what is the number of parameters, etc. Okay, so if these three information are provided, we do two stages of model compression. One is the first we call as the coarse exploration stage, where we try to explore the different bottlenecks in the model. Okay, so for a given model, we automatically, and okay, before going further of this, let me set the context. Okay, so Deeplite has built this engine called Neutrino engine, and this Neutrino engine is a complete black box framework. Okay, there is no human intervention at any stage in the process. The end user provides this data to the framework, and the framework provides you the optimized model. There is no human intervention in this step at all, and that is what making this problem all the more interesting and challenging. That what we say is that you can provide us with any model in any data set, and we would provide you the compressed model. Okay, and we do a two-stage compression. The first is what we call as the coarse exploration, and in this stage what we try to achieve is we try to find the bottlenecks in the model. Okay, and by bottlenecks what we say is that, okay, in the whole model, this few layers or those few layers uh, uh, take the maximum size or the time in doing the computation. Okay, and in the second stage we try to slowly start reducing or compressing the model based on the bottlenecks. And the annealing step is very important here, because you have the end user has provided us with a very strict accuracy level which is acceptable. Okay, so if my original model is 90.5%, we have to make sure that the model that we provide them is not less than 90%. Okay, that is really important for us. If we provide them with the 86% accurate model or 87% accurate model, however good the compression that we provide, it is practically not usable for the end user, because they have very strict accuracy levels that they are expecting. Okay, and that is where this annealing really helps us, that we slowly start cooling down the compression, and every time we reduce the compression, we just quickly check on the accuracy and make sure that the accuracy doesn't drop below the 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 expected threshold that the user has provided. Okay, and once we have sampled this smaller architecture, we do one final round of training and provide the optimized model to the end user. So from something that is completely intractable solution, this is somewhere around little tractable solution that the end users could still see the optimized model in close to real time solutions. Okay.
So here's a quick question. So in this two-stage, three-stage pipeline, does the search look like NAS, neural architecture search, or
Um,
how would you qualify, or are there different kinds of search working together?
Yeah, so we do not do a complete NAS or an AutoML kind of technique. we do what we call as a much more constrained search. Okay, we extremely limit the search space, but at the same time make sure that the search space that we are searching is really optimized search space to achieve the target metrics. Okay, what helps us in narrowing down the search space is the target metrics that the user has already provided. Okay, the user has already provided that what levels of compression they want, what are the primary targets, the primary KPIs they are focusing on, what is the accuracy levels that they're expecting. Okay, so what this helps us is we can clip off a lot of branches, because if we start exploring in those branches, these KPIs are not possible to achieve. So in actually real time, we can clip off a lot of branches, and the search space that we are searching is very limited, and that is what will help us to achieve this optimized model in real time solution. And how do we find the branches and clip off the branches is the patented solution that we have.
Sounds good. Yeah.
Okay. Yeah. Yeah. So the way that we are trying to do is that the important question is how much to optimize without compromising the accuracy, right? And this becomes an exploration problem. And in this exploration problem, what we try to do is we do what we call as layer selection. Okay, and for each selected layer, which we call as a bottleneck, we use a transformation function to replace the original layer. Okay, in simple terms, it is something like this. Okay, if I find, say for example, the 50th layer in my model to be a huge bottleneck, what I will do is I will take the 50th model and replace this 50th layer. Okay, we replace that one layer with a very tiny CNN for that layer. Now this tiny CNN performs the exact uh, purpose or role that this one layer has to perform, but instead of having that really large big layer, I will have a tiny CNN performing the same role as that of the layer. Okay, and we will identify all the layers in the model that needs to be replaced, and replace those layers in the model with tiny CNNs. So basically, we take a large parameter in large parameter layer in a network and replace it with smaller number of parameters. This will reduce the number of model size, the number of flops it takes, the improve the inference time, and also reduce the computational complexity, of which the layers that I'm going to show. And if anybody is interested, I'll share the paper of this original technique that we have in IAAI this year. So IAAI is happens along with AAAI. In IAAI 2021, we got the best deployed system for this technique this year. Yeah, so I will share the paper with you. I did not want to really go into the mathematics in this particular talk, because that itself is a talk separately. So the idea of this talk is to give the bigger overview of model compression. But if anybody is interested, I'll share the paper, and we could have an offline discussion on top of it. Right, and these are the results that we have achieved on popular models. Okay, if you look at these models, okay, let's focus on ResNet 18. The way to read this table is, the first is the original model. Okay, the original model is about 76.82% accurate. It has about 42 MB in size. The number of billion MAC computation it performs is 0.55, and the number of parameters it has is 11.22 million parameters. The overall on memory size it occupies is about 48.43 MB, and its execution time is about 0.05 milliseconds. Okay, which is just the inference time. Okay, and if you look at the stage 2 performance. Okay, in all the experiments, the only constraint that we have provided for Neutrino to optimize is by saying that the accuracy delta should not go below 1% of my original model. Okay, so if my original model is 76.82%, my compressed model should not go below 75.82%. Okay, so yeah, sorry, I hope you can see my cursor. Yeah, if my original model is about 76.82%, my compressed model should not go beyond 75.82%. Like yeah.
Yeah, unfortunately, it's not showing up cursor for some reason, but yeah.
Okay. Yeah, but you could see the first few rows in the table. Yeah. Yeah, and what we have achieved is that in all these models you can see that the enhanced accuracy will not be more than 1%, so that the compressed model is always in the range of the original model. But in terms of model size, you can see that we have achieved some 12x compression, 10x compression, or 29x compression, right? Look at VGG19, right? The original model was 76.6 MB in size, and the compressed model is only 2.6 MB in size. And with only 2.6 MB, we are able to achieve almost equivalent performance as the original model, but reduce the model size and the computation and the parameters and the speed. Basically, we have improved on all the other metrics uniformly, but not compromised on the accuracy. I think I missed that information. Okay, all these models are trained on C400. Okay, so all these models are trained and tested on C400, exact same train test data. And for people who are interested, in the previous slide I showed that we have two different stages of model compression, right? Stage 1 and stage 2. You can see that, say for example, focus on ResNet 18, right? uh, uh, the original size of the model was 42 MB. The stage 1 compression produced 7.5 MB in size, a model of size 7.5 MB, and stage 2 produced a model of size 3.4 MB, right? Yeah, so that is what we're trying to achieve. In stage 1 is sort of a course exploration where we try to do one quick round of optimization, and stage 2 is more of a deep search where we go and do annealing to try to compress the model further within the same thresholds of accuracy that we have. Okay, and we have achieved similar kinds of accuracy on other models also: DINSNet 121, GoogleNet, MobileNet v1, whatever model that you are trying to see. We have constantly optimized on all the parameters without reducing the accuracy more than 1% of the original model. Okay, and even on large data sets, say this is the ResNet 18 model on ImageNet 16 or Visual Wake Words, we can see that the ResNet 18 model on larger data sets is compressed to about 23 times the original model, right? Like a 42.6 MB model is reduced to 1.8 MB model without reducing the accuracy of the model, and the accuracy reduction is less than 1%. And in this application, it is applicable, right? 1% reduction is okay. You can even put give an accuracy reduction of 0.1%. Neutrino will still most likely give a compressed model of reduction of 0.1% accuracy. Right. So these are some results on some benchmark data sets and models, but we want to go okay, and yeah, so this is this is the time taken for the compression, right? Like I was saying that we provide near practical applications to model compression. Say for example, ResNet 18. Okay, we achieved a compression of about 12x. The y-axis says that how much of compression we have achieved. Okay, we roughly about achieved 12x compression for ResNet 18, and we were able to return the compressed model. The overall time it took for us is roughly about 1.5 hours. Okay, so it is not 1 minute kind of a solution, but it is again not an intractable solution that takes 10 to 12 years. Okay, we take roughly about 2 to 4 hours for most of the model. GoogleNet takes about 7 hours to get the compressed model, and DenseNet takes about 14 hours to compress the model. Okay, and that's the kind of timeline that we're working on, which is still practical, right? What we are trying to say is that night before going to sleep, put the model for compression. While you wake up, you will most likely get a compressed model, right? Which is decent enough for a practical solution, right? And this is the comparison between stage 1 and stage 2, which I've already explained in my previous slide. That stage 1 achieves 40% compression, whereas roughly about 40% compression is achieved in stage 1, and the remaining 60% of compression can be achieved in stage 2. Also, the time taken for stage 1 is only 20 to 30% of my overall time taken, right? So it's basically of how much time you have. If you want to, if you have time only during dinner, you can do only stage 1 compression, compress model before dinner, and after dinner you will get the compressed model. If you have time to sleep over the compression, just put stage 1 and stage 2, sleep over it, and by morning you'll get the compressed model. Yeah, something like this, right? Okay.
This is totally awesome. There's so much fantastic details about the algorithm. There are a bunch of questions, and
So
I
can I take the questions after this video? I just play this video.
How reliable is artificial intelligence? It's a question that has come up a lot, especially with the rise of self-driving cars. Reaction time is a critical factor. Although the AI-enabled detection is good, it's not perfect. If that car was going a little faster, the outcome may not have been the same. Deeplite was created out of this need for reliability. Our technology enables AI models to run more efficiently by making them faster, smaller, and more cost-effective while maintaining accuracy. We leveraged the speed of the BlackBerry QNX platform for advanced driver assistance systems to gather video data, then applied Deeplite's AI optimization software to analyze this data more efficiently. With this combination, we created AI technology that can enable vehicles to react up to 3 times faster. Not only does Deeplite's technology make these cars safer, it also significantly reduces battery consumption, giving drivers a lot more time on the road. Trust Deeplite for AI in our everyday life.
Yeah, so this is a project that we did with in collaboration with BlackBerry AI to deploy in their self-driving car compilation. Nishant, could I just take 2 more minutes, not more than that?
sure, yeah.
And I'll put all the questions together.
Audience who's asking questions, please just hold on for some time, and Anush will be happy to answer all your questions. Yeah.
Yeah, so I'm just wrapping up the presentation. So I'll just show a few real world examples where we used it, and I'll be happy to take all those questions, right? And this was one of the questions that they asked about different hardware architectures. So this is an object detection model on a mobile phone which uses an ARM mobile based CPU, and we see about for object detection, right? We see about 10x speed up, right? And you can see that in below when we toggle between optimize and non-optimize, we could see a clear 10x speed up difference, right? It is really slow in identifying objects, but when we toggle to optimize mode, it's easily 10x faster in optimizing this. So that's what we're trying to achieve, that if you put a deep learning model into mobile phones, can it performs much faster than what is it today, right? And this is one use case where this is with a use case called Andes, and their use case was they had a RISC-V CPU core, and their on-chip memory was less than 256 KB. Okay, but they wanted to port a MobileNet V1 into that model, and the size of the MobileNet V1 was 12.8 MB, and but their on-chip memory size is 256 KB only, so they cannot put a 12.8 MB model into a 256 KB model. So they came to Neutrino, they used Neutrino, and they provided two requirements: that their target size, model size has to be less than 256 KB, and the accuracy drop of 2% is okay for them. Okay. To tell a little more about this RISC-V CPU course, it's a $40 chip and using only 3 watt of power. Using Deeplite's Neutrino, we were automatically able to compress a model to a size of 188 KB, which is like 70 times smaller than the original model, and also reduce the accuracy drop was less than 1%. Okay, so without any compromising the accuracy, we were now able to port these MobileNet V1 models onto every single chip that they're manufacturing that has RISC-V CPU cores. Okay, and there was this one more use case where we had this SSD 300 object detection model, which they had to port into NVIDIA's Xavier GPU with an accuracy drop of less than 1%. We reduced the model size from 56 MB to 4.8 MB, which is 12x smaller. Also achieved a 3x power reduction and 3x speed up with literally no drop in accuracy. Right, and this is a model of SSD 300 with a ResNet 50 backbone, and there was this one more smart manufacturing use case that initially had about 12 MB, but from a 12 MB model we were able to reduce it to 144 MB, which is like 89x smaller, and reduction number of parameters, and the accuracy drop was again less than 2%. And this is a manufacturing use case where they want to put this model into an ARM Cortex M4 chip, which is again 256 KB of memory chip memory, and they had to use this on CCTV cameras to check the quality of their production. Okay, yeah. So none of this would be possible without my excellent and proud team.
I'm not sure where the background.
Okay. Yeah, and thank you, and kudos to my excellent team for achieving whatever you achieved so far. I think Nishant, I'm done. I'll be happy to take all the questions.
Again, thank you. There's a, you could do a virtual applause. That's the best we can do. This is one of the most amazing talks I've heard on the cutting edge, compression research and technology, and I'm pretty sure everybody enjoyed that, and people are still eager to learn more. So let me go back a little bit and see what has not been answered. Are you working on only on CNN models, NLP transformer models?
The current solution that we have in market focuses only on CNN models or computer vision models in general. It could be any kind of classification models, OD models, segmentation models, post-reduction models, etc. But we do not yet offer a product support for NLP models.
And is that metric that I think you're mentioning accuracy, but accuracy is not the metric for different tasks. Like you have IOU and mean average precision. Are you shifting between them?
Yeah. So when I mean accuracy, it's generally the metric that is used to measure how good the model is, right? It could be MAP, it could be IOU, it could be anything. So they could basically provide the metric that they are using to evaluate a model and the delta of the metric, right? If my original MAP is say 0.75 and should not go below 0.74, they could show that the MAP delta is 0.01. That's all.
Okay. Are there any interesting difference between filters of the Deeplite optimized model and the original model? That is, do they look visually different from the filters of the original model? Visualization analysis, have you done that?
That is very true, and that is true for any kind of compression, not just for Deeplite's model. Okay, any kind of compressed model, the filters will have to look different than the original model because the filters have learned something much more or much different than the original model, right? So that happens for any compressed model, and for sure happens for Deeplite's model also. And in Deeplite's model, our architecture itself will look very different from the original model because what we eventually do is replace every layer with a smaller CNN, right? A tiny CNN. You can see that there will be a con, a pool, a tiny CNN, a pool, a tiny CNN, a pool, a con, a pool, a tiny CNN, and a pool, something like that. Okay, so the architecture will itself look a little funny, but it really is good.
Funny and rhyming too.
Yeah, for visualization, if you look at using a standard visualizer, the architecture, it will look something interesting.
It's very interesting. So,
Yeah.
but can you say anything more about the filters? I mean, traditionally the filters look like bottom filters have the edges and the higher filters have the shapes. Is there any pattern that emerges when you compress them?
Oh, nothing like that level, right? Because we are talking about so many different models here, and so many different models have so many different filters. It's very difficult. Eventually, the filters are learning something equivalent, and because they are learning something equivalent, they are able to get equivalent accuracies.
Okay, and Chakri wants access to your Deeplite optimizer.
Yeah, so I'll like to highlight one more thing. Right now, what we have is a trial version. You could just go to our website and sign up for a trial version. You'll get a trial up version that you can try out. But by end of March, exactly from a month right now, we are going completely open source, and you will get the complete community version, which you can use it for yourself. So we are releasing the community version with the source code by end of March.
Well, that is great news. Yeah, I mean, it would be great to have the world to be able to access the latest.
Yeah.
Okay, one Hetul has a question. Is the compressed model still FP32 or low precision?
Yeah, so there are two kinds of compression. Okay, one, we can combine these different compression techniques. I talked about 4 different verticals of compression. We can combine, say for example, pruning and then quantization. Okay, so pruning removes a few channels, and then quantization reduces the bit precision of some of these the remaining channels weights. Okay, so the results, in fact, what I have produced is without any kind of quantization.
Yes.
Okay, so the best part about Deeplite's compression is that what we call as this is what we call a software based compression. Okay, so this is purely playing around with the model's architecture itself, and once we have compressed and got these results using Deeplite's compression, we can do any kind of quantization on top of it to achieve another 4x more compression. So say for example, we got 12x compression using this technique. If we then reduce it further, we'll get 48x compression on top of it, because you have reduced from FP32 to int8. We offer that solution, but it is, as I told you, it's limited by the hardware capabilities. Not everybody is able to run an int8 model. So while providing your KPIs, you can always say what's your target hardware also, and we'll say that if your target hardware is int8 capable, we will reduce it from 12x to 48x and give you a 48x compressed model. Or if it is only FP32 compatible, we'll provide a 12x compressed model.
So very quickly, could you briefly enumerate the int8 or low precision capable hardware that exists?
Um, um, uh, Intel has a couple of architectures that is int8 capable. ARM is building one which is int8 capable, and there are lots of other companies and startups which are building their own customized hardware, which is not only int8 capable, right, but it's also 2-bit and 4-bit capable.
Okay, that's great.
So most of these int8 capabilities, I think Intel is one of the forerunners. They are having a couple of good compilers as well as a couple of good hardware architectures. But again, they are not completely. These are not open architectures or open compilers. So we may not be able to use a lot of them off the shelf. But we are getting there. Intel is doing some good job on that.
So you mean the compiler stack on top of those tools are new? They are yet to be built, or they're just old ones? But
to the best of my understanding, Intel has it, and it is not yet made public or open source. Intel provides it as a product for their clients and consumers. Yeah, so it's Intel product offering.
I see.
Yeah, that's the best that I know about that. But I read a lot of papers from Intel, and they're doing some good job on that.
That's great. Any other questions? I hope we managed to.
Yeah, let me
address.
quickly go through. I think Professor Sumit asked. Yeah, the results that I showed on the second slide was on ImageNet. I can quickly show those slides. Yeah. This has results on both ImageNet as well as VWW. So even on large data sets, we have got good results. But I'll be happy to take any further questions that any of you have. You could drop me an email, and I'll be happy to have an offline discussion or talk about any of these topics further. And I could quickly share the link of my paper for people who are still here.
So broadly, to summarize, there is a lot that you can do by combining these different verticals of optimization.
Yeah.
And Deeplite tool is exploiting that and has a clever solution that combines all of them.
Okay.
And if we had hardware which which can help us more, then we'll be even more better at this. Is
Correct.
that fair estimate?
Correct. So there are two kinds of problems we're trying to address. One is how do we optimize the software side of it, which is the architecture itself. So we call it software-based compression. So that is one set of problems. Other set of problems is what we call as hardware-based compression. That for specific hardware architectures, how do we even compress the model further and make it more efficient? So both these are two different problems, and just as a marketing anecdote, Deeplite is trying to work on both these aspects of the problem. So we are not focusing on only one. We try to optimize the architecture of the model itself to make it smaller, and also we enable it so that we can run it across multiple hardware architectures.
That's very good. Nishan, I would like to collaborate out. Chakri, can you just send an email at contact@offnode.co and I'll get back in touch with you. Thanks, Anush. There's this recent paper, and I think the recent paper is called Deep Neutrino.
Deeplite Introduction. Yeah.
Yes. Okay. Yeah, sounds good.
Yeah.
Anybody?
Nishant, I know I overshoot by time, but
It's perfectly fine. I mean, I'm glad that you are able to spend so much time explaining, and the audience is so interactive, and I'm sure they got so much to learn, which they wouldn't have got otherwise.
sure.
So our format is not restricted. Yeah.
Cool. And feel free to reach out to me. I can provide my email
Sure.
in case if you want to follow up on any of these discussions or have some questions or doubts.
Sounds good. If nobody else has a question, I have one final question, which is so again, the broader picture of it. So we are building these big models, and then we're trying hard to optimize it, and then what we find is that they can be reduced down to 2 bits, 3
Yeah.
bits.
Yeah.
So why go this roundabout cycle? Why not do it in one go? Is it possible at all to build smaller size model, train them in one go? How far is that technology?
No, I think that there is some theoretical understanding of this. That in fact, I can talk about this topic for hours and hours. Okay, I will just highlight on one particular thing. If you could just give me 1 minute. Mm.
Yeah, and we're going to invite you again to talk about the other hour. Yeah.
Yeah, this topic is one of my favorite topics, and I'll just pull up something. Okay, so recently Hugging Face for some NLP models, they came up with this technique that so there is this BERT models, right, which is very popular, and BERT models has two different architectures. One we call as the BERT large, which is really large, and there is BERT small. Okay, BERT base. Okay, so BERT base provides some 88% F1 score, and BERT large provides 93% F1 score. Okay, so what they did is they trained a BERT large and started compressing from BERT large. Okay, and the compressed models was much smaller than the BERT base, like 40 times smaller than the BERT base, but produced 91% F1 score, which is greater than 88% F1 score.
Yeah. So even that's going the other side and gaining still.
Yeah, there was this research paper also, right? Train and then compress. I think that's the title of the paper itself. Okay, so yeah, so I think this has some to do with some information theoretic understanding of over parameterization. Okay, so over parameterization helps us in better generalization. So if I take a really over parameterized model, train that model, it is much more generalizable, and from that generalizable model, I'll be able to distill it into a smaller model. But if I take a really under parameterized model and then train that model, it will not be that effective enough.
Yeah. So something happens when you add those parameters and explore a bigger space, and then you can come back. But you can't reach that space in one go.
At least with the existing optimization approaches, we are not able to achieve. Okay, that I think that's the fair statement to make. It is very difficult to say that the architecture will never be able to achieve that space. But with the existing training techniques that we have, we are not able to achieve that space.
Sounds very good. Yeah. So that's one of the biggest mystery to me. I hope that gets resolved.
If it is any consolation, Nishant, is a mystery to everyone, not just to you.
That's perfectly fine. I just wanted to resolve.
Yeah.
Thanks, Rajiv. I have seen that paper. Yes, that's a very interesting paper, and we are slowly going in that direction. I don't know how much time. So Well, Abhishek is asking, is Deeplite hiring? You missed that part.
Yes,
Yeah.
we are always looking for hiring and interns. So yeah, again, feel free to reach out to me if you're interested, and we could discuss further.
Sounds very good.
Yeah,
Yeah.
thanks for that question. I always miss to add these pitching slides and pitching information that we are hiring.
Yeah, but
Look at the blogs that we are writing. We are sharing much more information on blogs, much more detailed information about the techniques, the results, the model architecture. So Deeplite website has a blog series that I am personally writing. So feel free to look at the blog series also. And for hiring remote, non-remote interns full time, feel free to reach out to me in my email address that I provided, and we could discuss it further.
it's good. Yeah. Well, I think Rajiv has this final question. We'll just stop with that. How do you compare with Intel LPOT?
LPOT. Okay, that's a tough comparison, Rajiv, because Intel's LPOT is sort of a closed architecture. But if you're looking at uh, comparisons, right? Let me quickly show you one comparison, which I think everybody would appreciate a lot. Can you see the screen?
We can see. Yes. Now.
It's the paper.
Yes.
Okay. So in the paper, so these are some of the experiments run by our clients. Okay, not by us. So this is one of the farthest experiments that we could show. So one of the clients on MobileNet V2 model for ImageNet data, they tried to use the original model, Deeplite's Neutrino, Intel's Distiller, and Microsoft's neural network NNI is their product for model compression. Okay, yeah. So the clients try to compare these models. Okay, and as we can see here, that the original model is 80.9% accurate. The Neutrino provide 80.4% accurate, which is better than Microsoft and Ancoda's Neutrino distiller. But we were able to reduce the number of parameters by 58%, much better than both the other companies were able to do. Their products were able to do, right? And our size was also 2.4x smaller, which is much better than what other products were offering. And so is our the number of computational flops. Similarly, for one more use case uh, on VW dataset using TensorFlow's Lite Micro, we were able to retain the accuracy much more. If you look at TensorFlow Lite Micro, it reduces the accuracy by 4%, right? And that is what I was trying to highlight, that the existing solutions reduce the accuracy by 3 to 4% in most of the cases. But we reduce the accuracy by only 0.5%, while still provide a better compression than TFLM in terms of parameters and also in terms of model size, right? Model size, they were able to achieve only 14x, whereas we were able to achieve 58x, right? Yeah. So this gives you some comparison, and if it is of any consolation, all these experiments were run by the clients that we are talking with. They wanted to compare existing solutions out there by bigger companies compared to us, and they found us better, and that's why they are using us, these companies. Yeah.
Yeah, that should be very persuasive for your
Yeah.
other clients too. Yeah, so it's a great set of experience. Yeah. Okay, thank you again, Anush. This was an amazing session, and yes, it will take us time to absorb so much stuff.
Sure.
The talk is going to be on YouTube, and people can revisit and relearn from it. And audience, yeah, thank you for being an amazing audience, asking those very interesting, very pointed questions. And please feel free to like on LinkedIn and mention any feedback about this talk. And we'd love to be able to organize these talks. Thanks to amazing speakers like Anush, and thanks to amazing audience. So please contribute back and help us spread the word.
Thanks
Okay.
again for the opportunity, and I'll be more than happy to interact with you and the audience on any future occasion.
Thanks, sir. We are going to invite you. Yeah, again.
Thank you very much. Bye bye.
Okay, thank you. I'm going to close this session, and thank you everybody for attending. Yeah. Okay. Thank you. Bye.